just said rewrite, right? So all I'm looking for is, could you figure out how to rewrite this integral in terms of u? And it looks like every single group figured it out. So yeah, well done, beautiful. So this integral is actually a lead into what we're learning today. You haven't learned how to do this yet you already know. So we could just skip the lesson and go to a movie. But
Can we?
Yes.
okay. So u is x plus 3. Your du is dx. So we go in and we start rewriting. So this right here, that's u to the 1/2. And our dx, well, that's du. But we still have an x, right? This x right here has not been replaced. So when you've got stuff left over that has not been accommodated by your u or your du, you gotta do a little finagling. So how are we going to finagle this? Well, I got to figure out how to rewrite x in terms of u. If only I had an equation that related x and u. Why, I do, right here, right? So if u equals x plus 3, then x equals u minus 3, and I can replace my x with a u minus 3. Piece of cake, right? Absolutely. Now, if we were to go ahead and continue with this, what would you have to do before you could start integrating?
Multiply it out.
You'd have to multiply it out first, right? You have to distribute, and then you can integrate. Because you cannot, there's no product rule for integrating. It's not just this integral times this integral, right? You got to multiply the terms together first and then integrate. All right, good. So today we're doing section 5.5b. There are actually 3 parts to 5.5b, and we're going to do all 3 parts. The first part is called special case use substitution, which is what we just touched on, and we're just going to do a little bit more of that, make sure that we kind of understand how that works. Then we're going to learn how to approach use substitution with definite integrals, because we haven't done any definite integrals yet. That's going to be probably the main focus of the lesson. And then we're also going to just take 10 seconds and talk about integrals of odd and even functions. And then after that, we have a little bit of practice, and then we're done. Hopefully, there, bless you, will be some time left over. And in the time left over, we are going to at least get a good start on quiz 5.2. All right. It's the last lesson of the chapter, but not the last lesson of the unit, because on Monday we still have to do trapezoids, which are in chapter 7, but we're putting them in this unit. So on Monday we'll do trapezoids. It should be a fairly short lesson. I'm going to try to keep it not gigantic, but I am going to put some review in there because once we finish trapezoids, we're in let's get ready for this test mode, right? So we'll probably do a little bit of review, and I'm hoping we also might be able to finish those 5.2 quizzes on Monday. If we can't, we'll push them off until after break. But what is on Tuesday?
Big quiz.
Big quiz, right? Okay. All right. Are we ready?
Is it test Tuesday?
The test is the Wednesday after we come back. So we have 2, after you get back from Thanksgiving, you have 2 review days and then test. The first review day, honestly, is primarily going to be kind of absorbed by going over the big quiz. But then we also, I do have some games and some review worksheets that we'll be working on. So, all right. Good. Any other questions? Let's begin. Okay, so when you have to do what's called special case use substitution, well, all that really means is when your u and your du don't encompass all of the x's in your integral. And you got to do a little bit of work to cover the rest of the x's. So we are going to try to evaluate the integral. We're not going to try, we're going to do it. So we're going to evaluate the integral of x cubed times the square root of x squared plus 1 dx. So first thing that we always need to find is u. What's u?
X squared plus
X squared plus 1. So your du would be 2x dx. Divide by 2 to get rid of it because there's no 2's in here. So 1/2 du equals x dx. All right. So if I rewrite my integral, well, this part right here, that's u to the 1/2. Wherever you choose to write it, I'm gonna put it over here. All right. Now, I have an x and a dx that equals 1/2 du. So this x cubed, I have to kind of break it up and think of it as like x squared times x. If I think of it as x squared times x, then one of these x's and this dx can be equated to 1/2 du. So the 1/2 du takes care of one of the x's and the dx. So I get a 1/2 and a du. So everything that's underlined has been incorporated into the integral. I'm still left with an x squared. So now I've got to figure out how to rewrite x squared in terms of u. What does x squared equal in terms of u? Okay. U minus 1. So you go to where you equated your u's and your x's, and you just solve. So x squared equals u minus 1. That one worked out nice. If this was just an x and we had to square it, so you solve and you just have to square a binomial. Like you just, whatever you got, you just got to work with it. So x squared equals u minus 1. So now I can replace my x squared with a u minus 1. All right. Now, we have to integrate this thing. In order to integrate, you're going to have to do what? Distribute it all out. Go ahead and distribute and integrate. Get a little practice. Distribute. Do you distribute in the 1/2 or do you keep it outside? You put it in? Okay. I don't really care. To me, it's the same either way. So we have 1/2 u to the 3/2 minus 1/2 u to the 1/2 du. Everyone comfortable? That look okay? Okay, and then it's just your typical raise the power by 1, divide by the power. U to the 5/2 divided by 5/2 is 2/5. U to the 5/2. See it when you multiply it by the half, you get 1/5 u to the 5/2 minus, and then this would be 2/3 u to the 3/2. So you get 1/3 u to the 3/2 plus c. Are we done? Why? Put the x's back in. 1/5 times x squared plus 1 to the 5/2 minus 1/3 x squared plus 1 to the 3/2 plus c. Is that good? We're all good? Okay. Your current book in WebAssign, I'm pretty sure, I'm like 99% sure, accepts unsimplified answers like this. So I think you're good. So our old book didn't have an electronic homework, it just had the book. And so there was no like solution thing. All you got were the odd number answers in the back of the book, right? And so whenever they did these kinds of problems and they showed the answer in the back of the book, what they would do is they would pull a GCF out of each term. Since each term has an x squared plus 1 to the 3/2, they'd pull an x squared plus 1 to the 3/2 out, and then what's left would be 1/5 times x squared plus 1 minus 1/3, and then they would combine like terms. And so you'd look at this expression and you're like, that looks nothing like what I've got here, but it was equivalent, but students were always thrown off by that. But just know, like, I don't know, the College Board usually just leaves it. But if for some reason you're ever doing something like this, where you have the same kind of thing with just different exponents in all of your terms, remember, if it's multiple choice and you don't see your answer, think to yourself, is there a GCF that I can pull out and get an equivalent answer? But for now, I will tell you, on your test, this is great. On your quizzes, this is great. On your homework, this is fine. Like, all around, like, this is really fine. Okay. Okay, so, all right, let's try one more. Just give this one a shot. All right, let's walk through it. So, woo. All right. So, higher, what's the U? X plus 5. So what's our du?
Yeah.
It's just dx, right? So when we rewrite this, so the bottom, that's cube root of u. I'm just going to keep it as cube, I can't even say it, cube root u. But now, so that takes care of that. And then dx, that's du. So that's done. But I still have this x here. So, Michelle, what does x equal? U minus 5. You just go say, oh, if u is x plus 5, then x is u minus 5. So we have u minus 5. Every paper I saw got that, which was the hard part. But then a lot of people got stuck or made mistakes on the next part. So it's a good thing I made you evaluate. So when you have division by what's called a monomial, a single term, you got to divide each term first before you start. Now, some of you guys like to write this as u to the negative 1/3, bring it up and multiply. That's the same thing, right? You either divide by u to the 1/3 or you multiply by u to the negative 1/3. Potato, potato, doesn't matter. So, u divided by u to the first, divided by u to the 1/3, you subtract your exponents. 1 minus a third is 2/3. And then here we have 0 minus a third, so you have negative 1/3. By the way, I don't know if I saw a single paper with correct parentheses, so please make sure that you use proper parentheses. Okay. So now we can integrate, right? This we can't integrate. You can't just integrate the top and integrate the bottom and hope for the best. Just like you can't differentiate a top and differentiate a bottom, right? So that's why you gotta clean it up first. Okay, so now 2/3 plus 1 is 5/3, so you get 3/5 u to the 5/3 minus negative a third plus 1 is 2/3, so you have 3/2 times 5, which is 15/2 u to the 2/3 plus c. So your answer would be 3/5 x plus 5 to the 5/3 minus 15/2 x plus 5 to the 2/3 plus c. Okay, good. All right. Questions? Cooper, how you doing?
Doing good.
Yeah?
Yeah.
Okay. All right. Hi, Ari.
Hi.
How's it going?
Oh, well, how are you?
I'm good. Seeing a lot of yawning today. Everyone seems tired today. It's a long week. Yeah.
We need rest.
Good. You need rest? Well, you're not going to get it yet. Okay. Okay. So this next part, there's a whole paragraph about it. I don't want you to sit there and spend all this time typing it. So I'm just going to talk you through it and I'm going to hide it. Okay. Okay. So use substitution with definite integrals. Use substitution with definite integrals. There are two methods, mathematical methods for approaching these problems. Both are perfectly valid. They're both correct. One is not only a bit faster, but it is also required that you know it for the AP exam. Now, the College Board never, ever, ever says, use this method to do this, ever. What they do, if they want to check to see if you know a method, is they write a problem that forces you to know the method. So that's what they do. Every year in the multiple choice, they have a U sub with a definite integral, and they ask it in a way so that you have to know the method I'm going to teach you, or you won't get the point. So anyway, so because of that, I always teach this the same way, and I always have at least a handful of students who don't want to do it. I don't know why. They just don't. And they want to rebel and do it the other way, and I hear the words, can't you just, right? I used to hear that so often, I used to call it one word. I thought they should add it in the dictionary, can't you just. Yes, you can just do the other way. However, you're going to miss at least a point on the AP exam. And the way that you're going to learn right now, you're going to need to know when you all take Calc 3 next year, right? So, because it's going to help you when you get into Calc 3. Because you're all taking it, right? Of course. Yes. Everyone is taking it. Everyone. Especially the girls. Not that I don't want the boys. I want the boys too, but I really want the girls, right? Okay. Is it okay if you take it in college? Of course. Yeah. All right. Okay. So let's get started. So we're going to walk through. I'm going to show you the method, and you're going to learn it. You're going to do it. You're going to love it. You ready?
Yeah.
Yeah. Okay. All right. What's your U? 2x plus 1. Oh, okay. Okay. All right. So our du is 2dx. I don't have any 2's that are out front, so I'm going to divide that 2 out. All right, so I'm going to bring this down a little bit so I can reach it better. All right, so what have I got? I have this guy right here, that's u to the 1/2. And then my dx is equal to 1/2 du. So I'm going to replace the dx with a 1/2 du. So far, just normal, right? So here's the thing that becomes so important to know, not just for AP exam, but for everyone who's taking Calc 3 next year, because right now, Calc 3 students are knee-deep in triple integrals, right? So here's the thing. This is why this is really important. This guy right here, this dx, this tells you what variable is represented by these numbers. So when this is dx, that means that these are x values. If you rewrite your integral in terms of u, your limits have to be u values. They can't be x values. If you write x values on an integral with u's, it's nonsense. You've just changed the whole problem. So you have to change your limits to u values. For some reason, some students just don't like doing this. It literally takes 4 seconds. It's so fast and so easy. So if you do it, it's so easy. How do you change your x's to u's? You literally plug the 0 in for x and find what is u. So, yes. So if x is 0, u is 1. Okay. If x is 4, what's u? 9. Does everyone understand how people are getting 9?
Yeah.
You plug a 4 in for x, and you find your u. All right. Are we ready to continue?
Yes.
Okay. So now these are u values. You don't have to write u equals. I'm just doing this so that like people in TV land that are watching can see. But as long as we've got a du, these have to be u values. You don't have to write the u equals. It's just for people to see. Yes.
Could you maybe keep it all as a general integral and then like put it in later?
You're doing the can't you just. Okay. So that's okay. See, it's good. It has to cut. We got to flush it out, right? So you haven't seen how wonderful this is going to be though. But the can't you just rewrite this without any limits? Just do the general the indefinite integral, right? Find the indefinite integral, do your u sub, right? Convert back to x's, and then write your limits at the end, plugging in the 4 and plugging in the 0, right? Yes, you can do that. That's mathematically correct, and it will work. However, you have to know this method for a number of reasons going forward. So I don't want you to do that. But yes, you can. It is also slightly longer. Want me to show you why? Here's your gift, all right? Yes, thank you. Okay. So first of all, let's do the antiderivative. So this becomes 2/3 u to the 3/2. So you get 1/3 u to the 3/2 from 1 to 9. We have a perfectly good integral to evaluate. Do we have to switch back to x's? No. Just plug your numbers in and you're done. So if we plug, so you never have to convert back. Because you've already converted your limits. This is an equivalent integral. You just said this and this are equal. So you can go ahead and evaluate this. So you have 1/3 times 9 to the 3/2. 27, right? How do you get 27? When you do 9 to the 3/2, you always do what first? The root, right? So the square root of 9 is 3, cubed is 27. Minus 1/3 times 1 to the 3/2, which is just 1. Yes, you can leave it unsimplified. I'm going to go ahead and combine the fractions if that's okay. So I'm going to read 27/3 minus 1/3 is 26/3. Okay. No, it's really not, right? It's really not that bad. So when you have a u sub with a definite integral, you convert your limits to u values, and then you just integrate with u, and you're done. You never have to go back to x's. By the way, if you do go back to x's, plugging the numbers into the x function is always more complicated than plugging the numbers into the u function, because you've simplified your function by converting it to u's. So you'll get the same answer, but it's going to take you longer. All right, let's see what you can do. So here we go. By the way, this is both a special case u substitution with a definite integral change of limits. Okay? So special case u substitution with a definite integral where you change your limits. I think you can do this.
I think we can.
Yes. Freeze. Okay. So, walking around a little bit, here's what I saw. I saw everybody got the correct u, and everybody got the correct du, and just about everybody wrote this down. But then when you were rewriting your function in terms of u, a lot of people forgot to transfer this 1/2. So be so careful. So first, this guy on the bottom, so, I think I'm just going to rewrite right now. So this is root u. All right. The dx, that's why when I'm rewriting in terms of u, I kind of underline as I go so I know. Like, there is thought. It's not just a scribble through. There's thought. Like, all right, I've rewritten this. Now I'm going to rewrite my dx. What is dx? 1/2 du. So 1/2 du. Now I've got to rewrite my x. So what does x equal? Well, x equals u plus 1 over 2. And so we have another 1/2, right? I'm going to write it kind of messy first and then clean it up. So what does this equal? So you end up with a 1/2 times a 1/2, or a 1/4. You know what? I'm going to write multiple steps. I don't want to get you guys confused. So you have 1/4 times u plus 1 over root u du. So I just put the two halves together. All right, now we got to divide. It's monomial. So u over root u, that's u to the 1/2 minus a half, or 1 minus a half. And then 1 minus a half is negative a half, so we have plus u to the negative 1/2 du. All right. So, I never did my limits. I got so excited about the halves. All right. So let's go to write our limits. If x is 1, what's u? 1. If x is 5, what's u? 9. So what you can conclude from the last problem and this problem is that every single u limits are always 1 to 9. Yes. Yep. Okay. No, that's not true. It's just coincidence. Okay. That would be an example of what kind of reasoning? Inductive reasoning, right?
Yeah.
Yes. Inductive reasoning is the type of reasoning where you make conclusions based on a pattern. Okay. All right. Okay. So anyway, so there's our limit. So now we have, this is 2/3 u to the 3/2. So we have, I'm going to just write 1/4 times 2/3 u to the 3/2 plus 1/4 times 2u to the 1/2. Evaluated from 1 to 9. All right. So now let's have some fun with fractions. So this becomes 1/6 times, hey, what's 9 to the 3/2? 27 plus 1/2 times 3 minus 1/6 times 1 plus 1/2 times 1. All right, so you have, now, can't you just leave it unsimplified? Yes, you can, but we're going to simplify, just because we also can. All right, so 27/6 plus, so 9/6 minus 1/6 minus 3/6 equals 27, 36, 35, 32, 32 over 6, or 16. Okay. Woo! Oh, we are like raising the roof right now. All right, good. Yes, all right.
Is that what the project is about?
Oh, yeah, that's a reference to u substitution. Yeah, to just do it. Yeah. See the one up high says just do it. Calculus. Yeah.
What is it like? Is it just
Have you ever heard the expression "just do it"?
Yeah.
Yeah, it's just a play on that with du instead of the word do. Yeah. Right. Okay. All right. Okay. One more. Quiet, please. One more with trig. Now, you love trig. Yes. Okay. I'm going to tell you your emotions. You love trig. So when you do u sub with trig, sometimes the u is just the argument of the trig function, the input, and sometimes it's a whole trig function. And it varies from problem to problem. So you have to be aware, is my u going to be just a 2x, or is my u going to be an entire trig function with a 2x? It could go either way. Depends on the function. What I usually do when I'm looking at trig is I kind of mentally, if I replace all these with just u's, I ask myself, do I know the antiderivative of cosecant u, cotangent u? If the answer is yes, then that's my u. My u is whatever the argument is, right? If my answer is no, then I got to do something else. So that's how I kind of do it, is I mentally think, well, if these were u's, could I integrate it? And if yes, I could, then yes, those are my u's, right? So go ahead and do your u replacement and see what you can do with this. There are, as I was walking around the room, there's a couple different approaches to this, and they all work if you do them correctly. So I personally would have just let my u be 2x, and that's what I'm going to do here. But I did see one student successfully rewrite this function all in terms of sines and cosines. and do a u sub that way, and it works. So what if you forget the antiderivative cosecant cotangent, right? So that's why one thing you could do, right? Okay, but anyway, so I personally, I would let u equal 2x, so du is 2 dx, 1/2 du equals dx. It's not even a special case, it's just a regular old rewrite. So this is 1/2 cosecant u cotangent u du. All right, we got to convert the limits. If x is pi 12ths, u is 2 times that, so u is pi 6. And if x is pi 4ths, u is pi halves. Now we have to think, what function has the derivative of cosecant cotangent? Negative cosecant. Negative cosecant. So this becomes negative 1/2 cosecant u from pi 6 to pi halves. Cosecant is the reciprocal of what function? Sine. Sine. Cosecant is the reciprocal of sine. It's okay. So I've never memorized a cosecant value. I know my sine values, right? So I just think sine and then flip it. So sine of pi halves. Anyone know the sine of pi halves? 1. So the cosecant would be also 1. Be careful, it's minus negative. So be careful with your negatives. Minus negative. Okay. Sine of pi 6 is 1/2. So cosecant is 2. So you end up with this. So you end up with negative 1/2 plus 1, which is positive 1/2. All right. Now, we still have one more little lesson to learn and a review. Before we do this, I want to teach you a trick. I, honest to God, don't know if Ms. Grunwald's going to teach her students this trick. I think I'm going to tell her today that I'm teaching you the trick. You don't have to use the trick ever, but it will help you save you a little bit of time. And if you start getting comfortable with the trick, it will save you a lot of time, especially next year when you all take Calc 3, right? Okay, so here's the trick. If your u is linear, do you know what linear means? Okay, all right, but how to recognize it if I give you a function? It's ax plus b. Number times x plus another number, that's linear. Right? So if your u is, for example, 2x, right? Or 2x minus 1, or 2x plus 1, right? Okay. If your u is linear and it's not a special case, it doesn't work on special cases, but if your u is linear, you can do the antiderivative, you can do the integral without a u substitution. So, and it saves you a lot. So, but wait, I don't teach this until after you've learned u sub, so you get comfortable with u sub. But if your u is linear, then what happens is the antiderivative is exactly the same as it would be normally if it was just x instead of 2x plus 1. You just have to divide by what I call the slope. The slope is the number in front of the x. So I'm going to do this problem real quick. This is the integral from 0 to 4 of 2x plus 1. 0 to 4 root 2x plus 1 dx. Okay. So think of it as like, okay, I look at my guts and I say, oh, my guts are linear. So the antiderivative of guts to the 1/2 would be 2/3 guts to the 3/2, except I got to divide by the slope of the guts, evaluated from 0 to 4. And then you just plug in. So if you have an argument that's linear, you don't have to do a u substitution. You can just do your normal integral as you normally would, keeping the integrand the same, and then just divide by the slope. So this would be 1/3 2x plus 1 to the 3/2 from 0 to 4, and you just plug in. So it's a nice little shortcut. You don't have to use it. You can always do a U sub, and life is good. But, for example, I'm going to skip to the last slide here. For example, oh, yes, Al.
Is there a reason why you divide by the slope?
Yes, because if you did a U sub on a linear argument, what happens every single time? Your du is the slope, and so you end up dividing by the slope, right? So you're just kind of cutting out the middleman and saying, you know what, I'm just going to jump and take my same function, just divide it by the slope. So if your u is linear, you can skip the whole u sub, just think guts to whatever, do the antiderivative with keeping your guts the same, and just divide by the slope of the guts. And so anyway, it only works for linear though. Some people get so good at u substitution that they can kind of do the whole like u du dividing like with exponents and everything mentally. I can't do that. I've never gotten that good. I just use the shortcut for linear. Did you have a question?
Yeah. Does the AP test or AP like college board take?
Oh, they don't care.
Oh, they don't.
Nope, don't care at all. Oh, by the way, quick question. How does the College Board check to see if you know how to substitute limits? Here's what question you'll get on a typical AP exam multiple choice. What they'll do is they'll give you this, and then they'll give you this with like a little A and B, and then in the choices they'll say A equals this and B equals this, or A equals this and B equals this, right? And you'll have to pick. They'll test to see if you know the new limits, right? Instead of can you evaluate the integral, can you change your limits, right? Which is easy peasy, but you got to know how to do it, right? Okay. So this was, I'm going to rewrite pi 6 to pi halves. Okay. So going back to that last slide. So if we were to do the antiderivative of 8x minus 7 to the 9th dx, go ahead and write this down. We're going to just do it together. Shortcut. Remember, you don't have to do shortcut. You can always do u sub. U sub is safe, right? You can always be safe. All right. So normal integral for 8x minus 7 to the 9th would be 8x minus 7 to the 10th divided by 10, right? Plus c. But you got to also divide by the slope. So you end up with 1/80th 8x minus 7 to the 10th plus c. Isn't that nice? It just saves you a little time. You don't have to write u equals du equals. Well, how do you do an integral of guts to the 9th? Raise the power by 1, divide by the power? Yeah. So anyway, it's just like a little mini trick. Just saves you, yeah. It's just a little time saver. No, you can do a definite. Then you're definite, you wouldn't change your limits because you'd always be with x's. So, anyway. Okay, before we do the rest of these reviews, there's one more little topic I got to teach you, and that's symmetry. All right. Yes? So Friday, our only brain break is that I give you music, and I will play music while you're working on your quizzes today. Why, do you want a separate brain? I don't know what brain break to give you besides that. Oh, you didn't get any bad jokes?
Yeah.
All right. So we have functions are odd, even, or neither. An even function is a function with y-axis symmetry. So y-axis symmetry means that your f of negative x and your f of x are the same. So you have the same stuff on both sides of the y-axis as you go out. When you have a function with y-axis symmetry, if you find the integral, if you find the integral from negative a to a, well, that would be the same thing as finding the integral from 0 to a and just doubling it, because you have symmetry. Does that make sense? Okay. So when you have an even function, if f is even, then the integral from negative a to a equals the integral from 0 to a times 2. How do you know if a function is even? If it's a polynomial and all the exponents are even, then it's an even function. Just so you know, constants are even if it's like a constant of 7, because it's like 7 times x to the 0. And 0 is an even number. So polynomials, if all the exponents are even, if with or without a constant, the function's even. Odd functions have origin symmetry. Origin symmetry is a point symmetry. So a point symmetry is not over a line. This is line symmetry over the y-axis. Point symmetry is a rotational symmetry. What that means is if I stuck a pin in the origin and spun the function around 180 degrees, would it land back on top of itself? So if it would land back on top of itself, then it is called an odd function, and it has origin symmetry. So an odd function, if it's a polynomial, all the exponents will be odd, and there will be no constant. So the other way, by the way, so first, so when you have an odd function, you always have the same amount of graph below that you have above. So the integral from negative a to a will always be 0, because they'll always wash out. Trig, cosine is even, right? Just think about cosine, right? Cosine looks like that. Cosine's even. Sine is odd. So if you ever have an integral, say like negative pi halves to pi halves on a cosine, you could just do integral 0 to pi halves and double it. If you have negative pi halves to pi halves on a sine, you know it's 0 and you're done. So it's just a little note about odd and even functions. So I have 2 quick examples, and then I think we might call it a day, because I want to do some other stuff. So x to the 6 plus 1, is this odd or even? This is even. And since this is even, we can rewrite this integral as 2 times the integral from 0 to 2 of x to the 6 plus 1. So you end up with 2 times, so 1, 7, x to the 7 plus x. Just so you know, if you have a definite integral and you're writing brackets, you don't have to write the vertical bar. Most people just stick the numbers on the bracket and call it good. So that's fine. Okay. So anyway, so we have 2 times 2 to the 7th, 128. So we have 128 sevenths plus 2, and then minus 0, because you just plug in the 0, which is nice. Plugging in 0 is nice. So all this does is it allows you to make your life a tiny bit easier because you get to plug in a 0. It helps you a lot when you all take Calc 3 and you have to do all these crazy volumes, but there's symmetry, right? Like right now, just this morning, I was working with a kid on a problem where they had to find the volume of this space, right? It's a sphere with a cylinder cut through it. And so I'm like, well, let's see. Well, first, let's just slice it here, do the top half, because we have symmetry, so we just do the top half and double it, which is so much easier, right? So when you get into funky problems, symmetry can be a really good friend. Okay, last one. Tangent over 1 plus x squared plus x to the 4th, they're telling you it's odd. There's a whole thing that you can investigate, not now, about like odd times odd and even times even and even times odd and even divided by odd and odd divided by even. Which one is it? Is it even? Is it odd? Right? So anyway, this one's odd. Tangent is odd. 1 plus x squared plus x to the 4th is even. Odd divided by even is odd. So, if we were to evaluate the integral from -1 to 1 of this big giant function, what would the answer be? 0. Done. Yay. Right? Okay. Yeah, odd functions are nice. All right, there are some examples of just extra practice problems, but instead of doing these, I'd like to start working on quiz 5-2. So I'm going to pause. I'm going to do these while you guys are working on quiz 5-2 so that they're on the video. If you want to try them yourself, you're welcome to do it. Okay, so for this one, I'm going to skip the u sub since it's a linear argument. And I'm going to think 5x plus 2 to the 1/2. So that would be, I'm just going to erase this here. Okay, so we get 2/3 times 5x plus 2 to the 3/2, but then I have to divide by 5 because of the slope. So what do I end up with? I get 2/15 5x plus 2 to the 3/2 plus 3. All right, this guy I got to do a full u sub. U is 3x squared minus 1. Du is 6x dx. I want to get a 4, so I'm going to multiply each side by 2/3. So 2/3 of u is 4x dx. So this guy equals the integral of u to the 4th times 2/3 du. So you end up with 2/3 times 1/5 u to the 5th plus c, which equals 2/15 times 3x squared minus 1 to the 5th plus c. All right, next one. You have to choose cosine because it's raised to the 5th power. So your u is cosine. Your du is negative sine. So this guy equals the integral of -5 u to the 5th du, which is -5 6 u to the 6th plus c. So your answer would be -5 6 cosine to the 6x plus c. Last one. Your u is 5 minus 2x to the 4th. Your du is -8x cubed dx. Got to get rid of the -8. So we end up with the integral of, so -1/8 times u to the -2nd du, which is -1/8 times -u to the -1st. So you end up with -1/8 times 5 minus 2x to the 4th plus c. And that's it.